Hello everybody, this is Susana Molekin, and as many of you know, I have a master's in physics and astronomy, and I had been a physics instructor for almost 24 years. Oof, long time. But anyways, I decided, I was going through all my PowerPoints and decided that I have put videos of different metaphysics and different sciences on the Real Genius Show. But it's kind of funny that given that I have a master's and my background is actually as an astrophysicist, that I didn't put anything in astronomy. And so I decided to go through all my lectures. And as you can see, this is going to be my first lecture that I'm going to put in YouTube. And you will see that I have, like this one, for example, was for a class that I taught in 2009. Wow. For Pasco Hernando Community College, which is now Pasco State College or State University, which is a great college, has different campuses. But anyways, what I'm going to do is I'm going to put several of these astrophysicist presentations, and this is astronomy 102, which will be like a basic astronomy for undergraduates, but I figure maybe kids are in 3rd grade, 5th grade, they might like some of the stuff. And so I'm going to explain, I'm going to do a review knowledge of some of the algebra and things that we use for astronomy. We do use a lot of math for astronomy, but normally on the beginning courses, we don't put a lot of emphasis on the math in itself. We're just more doing vocabulary definitions and explaining concepts. And so here it is. This is my review knowledge to get you ready for a beginner class in physics as an undergraduate, or maybe astronomy or other science. So here we go. So obviously we're talking about astronomy and how big is the universe. And the universe is very vast. Vast means big, right? We're gonna look at our location. I'm gonna show you some pictures of where we are located in the Milky Way. It's a galaxy called the Milky Way. And we have a limited view from where we stand of our observable universe. What is the observable universe? Well, I'm gonna show you later that we're pretty much stuck inside of a huge box. And the observable universe from our standpoint is less than 0.1%, much less than that. And that's that we live in a corner of one of the arms of the Milky Way. And because of where we stand, our solar system stands inside the Milky Way, it's very difficult for us to be able to look outside. And so our observable universe, which like I said is pretty much 0.1% or less of the whole universe that we know, is very, very limited view. So we inhabit the planet that whirls around a star. It is part of a solar system of planets. It is located on one spiral arm of our galaxy. We're pretty much a very tiny dot in a spiral arm of a galaxy which drifts through a vast space composed of billions of galaxies just like ours. So we're pretty small. Now I know that some of you already have seen pictures like this. This is obviously basic astronomy. Probably you're super advanced on this. But I wanted to go through the differences because there are kids that sometimes confuse the stars with planets and other things. So a planet, the biggest planet of our system is Jupiter, and it is what is called the gas giant. And of course, we also have asteroids like Eros, for example. And asteroids are different kinds of asteroids. Some of them are rocky. Most of them are rocky and metallic debris. But there's 3 or 4 different kinds of asteroids depending on the composition of the asteroid. So some asteroids are more rocky with chondrite and carbon, and others are made with metallic debris. We also have comets, and comets are rocky and icy debris that goes through the universe, and most of the comets, of course, have what we call trajectories. They follow the same trajectory or the same path. Some of the comets come back into an elliptical orbit, like the Halley's Comet over every 75 years or so. And then we have the sun, and we'll see that the sun is a star, is our star, and it's a yellow star, and it is called a G2b star. So as the stars go, it's pretty average compared with other stars. So we don't really have a star that's really big, but it's not a small either. We're kind of average with the rest of the observable universe. And of course, we have interstellar gas and dust. And it's very beautiful. You can see how they take pictures of different Eagle Nebula, for example. The nebulas are very beautiful. They have different colors. Now, most of these pictures are done by artists. Of course, they're trying to do renditions. Sometimes they take pictures of the same nebula or the same planet or the same galaxy, and then they put the pictures together with photography to make them look better. But literally what the colors mean is every chemical has a different color. So, if I was going to guess, I would say, okay, this nebula has more orange and yellow, probably has more potassium, it has more sodium, blue is fluorine. So every chemical displays with light a different color, and we'll talk about that later. Okay, so how about the galaxy? So galaxies can be of different forms. Our galaxy is very similar to the pinwheel galaxy that you see in here. M51, which is the Andromeda galaxy, our galaxy, which is the Milky Way, and the pinwheel galaxy, all of those are, they sound like they go on a spiral, right? They have arms that are spiraling through. And what you see on the arms is interstellar gas and dust. And that's why if we imagine that we are in one of the arms of the galaxy, that's why it's so difficult for us to be able to see what is farther in the universe, because there's so much gas and dust in our way, towards looking in front of us and behind us, okay? There's also black holes in the universe. There is a black hole that's really close to us in the constellation Sagittarius, and next to what is called the Magellanic Clouds and cluster. And everybody knows what a black hole is. Pretty much, it's called, you see it in the middle is a singularity. It's called a singularity. And what a black hole does, it just eats everything on its way. Everything that's around it. It gets fed by gravity and everything that's around it. And as you can see, Hercules is in a cluster of galaxies. So cluster galaxies. So galaxies, gravity tends to pull everything together. And so gravity is putting all the mass together of the universe. So sometimes, even though the observable universe tends to follow a rule in which pretty much everything is homogeneous per se, we call the law of homogeneity in astronomy, but you can see that obviously there are a lot of things around. Planets, galaxies tend to attract to each other just because they're pulling on each other with gravitational force. And of course, every galaxy also has interstellar gas. As you can see here, we have 3 galaxies, and in between them, even though they look like little tiny points, there's a lot of interstellar gas. Sometimes galaxies eat each other up. They're called cannibal galaxies. So let's look at our location. This is a picture of the Milky Way, and you can see where the sun is located. And where the sun is located is called the galactic bulge. And over time, people have been giving names to the arms of the galaxy, depending of just to understand our location. You can see Sagittarius arm, Perseus arm, the outer arm. And so the local arm is you can really see that inside the local arm is where our solar system is located, and Earth, of course, is located there. So as you can see, it is very difficult because of our location. If we go look towards the center, then we have the sun and all that interstellar gas and dust. It's very difficult for us to see what's on that side. If we look to the other side, we still have a lot of dust and gas also. Now, astronomy changes the way that we look at our world. And most people think, when they think of astronomy, they think of the very big, the galaxies, the moon, the sun, the planets, but also astronomy studies also the very small, the micro, the particles that are formed, and we'll study about, chemicals also during this course. But we also study particles as small as a millionth or a billionth of a meter, which is really, really small. I want to show you a comparison of a scale. And this is, of course, from a book from Freeman and Company, which is a very normal astronomy undergraduate book. But you can see that 10 to the minus 15, which is 10, and then you put 15 zeros in front of the 1 to make it small. So it'll be 0.0000014 times, right? That will be 10 to the minus 15th. That is the size of a proton. Now the size of a virus. Now unfortunately, we're going through the coronavirus pandemic. So how small is a virus? So most viruses are the size of 10 to the minus 5 to 10 to the minus 8, which means that there might be it might be 5 to 8 zeros in front of the 1. That's how small a virus is. We will learn later on chapter 5 or lesson 5 that viruses live in a different spectrum that we live. They live in a different area of the light, of the natural light. Human beings, which you can see here on scale 1, we're taking that as a baseline. Baseline means we're taking that as our kind of rule, we're the starting point. We live in what is called the visible spectrum, or the light, right? Our yellow light from our sun. And bacteria also live in the visible spectrum, whether viruses do not. Viruses live in what is called the UV spectrum of light. All right, so we follow with the diameter of the Earth, the sun, distance from the sun, and you can see how the number 10, which you will learn later, is called as the number on top of the 10 is called an exponent, and then the number 10 is called the base. And so the number 10 is the number of times, obviously, is the exponent. So we do 10 to the 5th will be 10 times 10 times 10 times 10 times 10, right? 5 times. So as you go farther out from the Earth into the universe and past the solar system, we can see, look, 10 to the 15th is the distance to the nearby stars. The closest star to the Earth, it is called the Andromeda galaxy, and it's 4.2 light years away, which means it's 4.2 years away from us. And then the diameter of the galaxy, as you can see, is 10 to the 20th. And then as you go out, you can see the size of the observable universe and cluster of galaxies. So when we study astronomy, one of the most important things, of course, that we do is we measure everything. A scale is really important in a space. We go from the familiar to the world, everyday environment, to the vast space. We express distances with units that can account for such a vast space. And we measure distance in miles on Earth if we live in United States, maybe in kilometers if you live in Europe. But when it becomes when we're talking about space, measuring everything in miles and kilometers might not be okay, because these measuring distance between planets are really, really big. So, we're always dealing with numbers, of course, but we like to make calculations simpler for us, easier for us. So we're going to use numbers that maybe are in a scale that's bigger, but number that is smaller. And so before we learn about scale, I'm going to teach you a little bit about the systems. So we have two different systems in the world. One of them is in the United States, we use the the US system of measurement, but in Europe we use the International System of Units, sometimes called the Imperial System, and some people call it SI for short. That's an abbreviation. System of Units, System International. Now, it was developed in the 18th century of France, or so they say, and the International System of Units, from the French Le Système International d'Unité, is the modern form of the metric system. Now remember, this is a system that was supposedly developed in Europe. Now, Lavoisier was the person in France that was given credit for developing the System International of Units. However, if you study history, you will know that the person that actually came with the idea of the system of units was actually Benjamin Franklin in the United States. Now, the system is very convenient because it's based on multiples of power of number 10. It is the world's most widely used system of measurement, both in and every day. The SI system or metric system simplifies calculations and is used all over the world. It doesn't matter if you live in Europe or in the United States. If you work in healthcare, you're going to be working with the System International of Units. The System International of Units is based in three fundamental units: length, mass, and time. And it is based on a decimal system of numbers, which expresses quantities, changes from smaller to bigger, and vice versa. So, all of us know about unit conversion. I used to teach nursing, and when I used to teach astronomy, everybody will get really nervous about unit conversions and talking about the metric system of units. But in reality, we all know how to do unit conversion because we do it every day. We just don't realize that we're doing it. For example, everybody knows that a dollar has 4 quarters. That is unit conversion, right? You also know that every hour has 60 minutes and every minute has 60 seconds. You just did conversion right there. So for example, when we talk about 1 hour, then 1 is the magnitude or the value, whatever you want to call it, and then hour is the unit of conversion. Now, when we're talking about astronomy, I told you before that you have to know what unit of measure is appropriate for your problem, because in a space, and when we're talking about planets and distances to other planets, distances are really big. We cannot really work all the time with miles and kilometers. We can try though, and we do have the conversion in miles and kilometers, as you can see here. But, for example, when you're talking about kilometers for distance from New York to California, or on high volcanoes on Mars, light years for distances across the solar system, we use something called astronomical units. An astronomical unit is the distance from Earth to the Sun. So that becomes our baseline. So what do you think is easier? Do you think it's easier to remember that 9.3 times 10 to the 7 miles equals 1.5 times 10 to the 8th kilometers? Or do you think it's easier to remember that the distance from the Sun to the Earth is 1 AU? and the distance to Jupiter is 5.2 AU. Well, I think it's much easier to do calculations with the smaller numbers like 1 or 5.2. Now let's learn what a light year is, because in this course we're studying a lot about vocabulary and definitions. A light year is the distance that light travels in a vacuum with absence of air in a year. Duh! Okay, we know that. But how much is a light year? A light year is 9.46 times 10 to the 12 kilometers, or 63,000 AU. Now I told you Proxima Centauri is 4.2 light years away. Now I know that a lot of these scientific, like Star Wars or Star Trek, they always talk about parsecs. Parsecs is actually a real unit, and in astronomy is the distance at which two objects separated by 1 AU make an angle of 1 arcsecond. So you can see here that we also have different conversions for parsecs. So 1 parsec is equal to 3.26 light years. 1 kiloparsec equals 1,000 parsecs, and 1 megaparsec equals 10 to the 6 parsecs. Now at the beginning, we won't be making any kind of calculations with this. This is just for you to know. So if you're an astronomy student, you really want to learn at least what is the definition of AU, and what is equal in miles or kilometers, and the definition of light year, because you're going to be using those two numbers. Now, I told you that in astronomy, we're talking about very big distances, and we're going to use something called scientific notation. You probably have seen over the past slides that we have numbers 10 to the 5th, 10 to the 3rd, 10 to the 1. All of that is called scientific notation. Scientific notation is a style of writing large and small numbers using powers of 10. It simplifies calculations and it also helps us to avoid mistakes when writing large numbers. In a power of 10, as I told you before, we have 3 different parts. One is called the coefficient, the multiplication symbol of the operator, and the power of 10 with the exponent. The exponent tells you how many places you move the decimal point to the right or to the left. You will move the decimal point towards the right when you're making the number bigger, for example, 10 to the 9th. You will move the decimal point to the left when you're making the number smaller, for example, 10 to the minus 9th. So, for example, instead of writing 3 billion, like you see here, and try to multiply that, we can write it as 3 times, count the number of zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, 10 to the 9th. I hope that makes sense. This is called shorthand. In scientific notation of powers of 10, the 10 is followed always by an exponent. If you don't see exponent there, like for example, you just say C10, believe it or not, there's an exponent there, you just don't see it. The exponent is 1, and 10 to the 1 is 10. Now, we have 10 to the 4th, and that's 10 times 10 times 10 times 10, which of course is 10,000. The superscript, or the little number on top of the 10, which in this case is 4, is called the exponent. We count the number of zeros and write it as a superscript, the number 10. So for example, if you see the huge number, and 1 followed by 10 zeros is written 10 to the 10th. This system is also used for numbers less than 1 by putting a minus sign in front of the exponent, like I told you before. Now, where did all this come from? Why are we studying all this? Well, I know that you hate this work, algebra. This word, everybody hates that word. But algebra, we use algebra for astronomy. And algebra has certain rules. So for example, any number divided by itself is 1. So if you have 10 to the third divided by 10 to the third, that will give you 1. Any number elevated to 0 is 1. So if you have 10 to the 0, that will be 1. If you have 7 to the 0, that will be 1. And we also have had to do multiplication and division with exponents and powers of 10. And it's very, very easy. Look at how easy it is. Let me explain to you. When a number with an exponent is multiplied by the same number, and you can see the base is always 10, right? The base has to be the same to be able to multiply. 10 to the 5th times 10 to the 7th. Then that will be 10. And then we add, when you're multiplying, you're going to add the exponents. So you can see the first 10 has a 5, the second 10 has a 7, so you're going to add both exponents. 5 plus 7 is 12. So your answer will be, the base is the same, 10, and then you will put 12 as your exponent. Now, do we do the same thing with division? No, we don't. So for division, we're going to do the opposite, which will be subtraction. So if you have 10 to the 5th divided by 10 to the 7th, then we get 10. We keep the same base, right? 10. And then we're going to subtract 5 minus 7, which is minus 2. A minus sign in the exponent of a number means that the number is actually 1 divided by what the quantity would be if the exponent were positive. Through 10 to the minus 2 is the same thing than 1 over 10 squared. Alright, now I know that some of you have done conversion before. And sometimes they will ask you to do conversion between two things that are in the US system. And then you probably have no problem. Other times they will ask you to do conversion using two things that are on the imperial system or the European system. And some people might have some trouble with that. And then another times they might have problems in which they're asking you to do conversion between both systems. Alright, let's look at some of these problems. On the first problem, they say, my telescope is 200 inches wide, knowing that 1 inch equals 2.54 centimeters. Now, 1 inch is an American unit, whether centimeters is a European unit. Okay, so how do we know that 1 inch is, they're giving you the conversion. 1 inch equals 2.54 centimeters. How many centimeters wide is my telescope? So what you have to do is you have to find out how many centimeters wide it is your telescope. So we put 200 times 2.54 over 1 inch, right? And we get 508 centimeters. Now another conversion. My telescope is 4 meters long. How many inches will this be? Okay, so now we can see that we have to pass meters to inches. Sometimes it is better to do meters to centimeters and then centimeters to inches. So sometimes you might have one step only when you're doing conversions. Other times you might have to do a couple of steps. So 4 meters times 100 centimeters over 1 meter times 1 inch over 2.54 centimeters. That will give you 157.5 inches. Now, since Babylonian times, when we're talking about angular, or you see something that has to be with an angle, that means it's a part of a circle. The circle has been divided into parts of a system that uses multiples of 60. If we are at the center of the circle, we consider it to be 360 parts as it stands all around us. Everybody knows that a circle has 360 degrees. This comes from Egyptian and Babylonian times. Each part is called a degree. Each degree, in turn, is divided into 60 minutes of arc, and each minute is divided into 60 seconds of arc. And that shouldn't be a surprise, right? Because pretty much if you want to remember this, just think about what an hour is. An hour is 60 minutes, right? And each minute is 60 seconds. So when you're talking about minutes of arc, it's the same thing than an hour, but just remember this is in a circle. So in 1 degree, we have 3,600 seconds of arc. And this is some of the definitions that you should know and that we have gone over before. What is a light year? What is a parsec? And what is an astronomical unit? I hope that you enjoy this presentation. Thank you so much for being with me, and I promise you the next presentation is going to be not so much math and much more exciting than this. See you soon.